Today, I will be presenting my research into robust decision-making for data-driven autonomous systems. Creating safe and effective autonomous vehicles is a concern automotive companies are looking into. Autonomous vehicles need to be able to identify stop signs and other obstacles. Otherwise, civilians could be harmed and trust in these vehicles would diminish. Even if the autonomous system is usually accurate, the system could be manipulated to perform incorrectly. Therefore, it is important to understand how an autonomous system works and how it can be manipulated. To understand how an autonomous system works, I designed a scenario where a vehicle, TurtleBot in my case, would go from one location to another. While moving, the vehicle should detect a stop sign and act accordingly. In order to do this, the vehicle relies on a neural network trained using past navigation data. The network then makes a prediction, and the vehicle stops if a stop sign is present. The goal is to analyze how accurate the network is and to understand the effect of malicious data on the system. To create the neural network, data is collected from 4 robot operating system topics, also known as ROS topics, corresponding to position, velocity, scan intensity data for the robot, and position data for the stop sign. Malicious data can replace this data and change the outcome. The classifier in the neural network uses machine learning to determine if the current data has a stop sign present or not. From there, the robot should decide to stop or keep moving based on the prediction. Here is a video showing the classifier in action. The stop sign we used is the black bar, motion trackers attached. The lidar intensity is shown on the map to the right. As the TurtleBot gets closer to the stop sign, it is detected on the map. TurtleBot gets close to the stop sign, stops, waits 6 seconds, and then proceeds to the goal. This happens because the predicted probability of a stop sign present exceeds the threshold of 40%. If there are 6 instances when the threshold is exceeded, this robot should stop as it does in the video. In this video, the robot moves without a probability threshold in place, like the previous example. Without the threshold, the robot will stop only when the network is 99% sure there is a stop sign. Due to this, the robot moves past the stop sign because it detects that 99% probability farther away than where we wanted it to intend to stop. With the threshold, this issue is alleviated and the robot stops in a safe location. Once the data has been collected, malicious data replaces different inputs. Examples include moving the stop sign's position and providing incorrect lidar scan intensities. In the video, the position of the stop sign is changed in the input data. The stop sign has been virtually moved 2 meters away. The probability threshold of 40% is still present in the video. The robot thinks the stop sign is not near it, so it doesn't stop near the stop sign and instead just goes to the goal. Here, the robot moves without the probability threshold and has spoofed sign data as in the previous video. As you can see, the results are similar to those seen with the spoofed sign data and the use of the probability threshold. The robot does not stop for the stop sign. To determine how accurate the neural network is in each scenario, the predictions of the neural network at specific time instances are compared to the label of a stop sign being present. Determining the accuracy helps to understand the effect adversaries and malicious data play on an autonomous system. To learn more about my research, please check out my poster.